This talk is aimed to give a general introduction about AFM possibilities and how we can use them, giving some brief examples. So, as you're well aware, in our ever miniaturizing world, our electrical high-tech devices become smaller and smaller. For example, in modern thin-film solar cells, we'll find 5 to 6 different functional layers over a span of below 1 micrometer. Or as we have heard today from Samsung, their model chip design are basically approaching the 3 nanometer regime. The same accounts for different field effect transistors, where we have to understand the different electronic properties on a nanometer scale. But I think the most prominent candidate that exemplifies our ever-progressing miniaturization are 2D materials that might pave a way to single atomic layers as the key, functional component in modern applications, be it, for example, 2D material gas sensors or pressure sensors, electronic sensors, or functionalized membranes, or any other kinds of systems. And all of them have in common that we need to understand, map, and ideally quantify different properties, be it the topography, the conductivity, work function, or mechanical properties. Thankfully, for that, we can use atomic force microscopy, since it allows us to understand and measure forces on a nanometer scale. So this is again a brief introduction. In general, we use a micrometer cantilever that acts as a force-sensitive spring. The rear end of this cantilever is equipped with a very fine and sharp tip, where the tip apex is usually only a few nanometers in diameter, or even below 1 nanometer. Any acting force on this cantilever will cause it to deflect either away from the surface due to repulsive forces or towards the surface due to attractive forces. However, we are not limited only to mechanical interactions. We can detect, as you're well aware, all different kinds of forces, ranging from electrostatic forces, magnetic forces, van der Waals, or Pauli repulsive forces. So this, in combination with the ability to also attach different kinds of lock-in amplifiers or current amplifiers, applying an external bias, give us the opportunity to generate a huge pool of information, ranging from electrical properties, as we've seen this morning, from capacitance or localized charges like surface potential, or even the current we can map locally. But we can also determine mechanical properties like the modulus or ITs of value, even thermal properties locally on a nanometer scale. So you could say that atomic force microscopy is basically the Swiss Army knife of microscopy. For today's talk, I'm going to talk briefly about KPFM and how does it work and how we can use it to monitor different applications. So in general, as you might well aware, we need a conductive cantilever and ideally a semiconductive or conductive material to get quantitative data for KPFM. When we take a look at the energy structure of these materials, we'll find that the Fermi level is well within the conduction band for both materials. When we now establish an electric connection between these two, electrons will start to flow from the material with the higher Fermi level to the material with the lower Fermi level, in this case from the cantilever to the sample. What we get in essence is a so-called contact potential difference, which will be achieved once the Fermi levels are aligned. And since we then have a net electrostatic charge between these two materials, we can measure an electrostatic force. This we usually do by additionally applying an electrical excitation, an AC excitation, with a given frequency FAC. And the amplitude of this excitation depends on the potential difference between these two. Our KPFM feedback now works in a way that we also apply a DC bias to counter this contact potential difference, which in essence means we apply a DC bias to push these electrons back to the original place, removing the charges. And when the amplitude of this excitation becomes 0, we exactly equate our DC bias to the negative contact potential difference. And this allows us to map basically the work function, for example, on a nanometer scale. Such measurements have been done, for example, at our place, measuring KPFM on molybdenum disulfide flakes on a silicon substrate. And for that, we used the very traditional and classic amplitude modulated KPFM mode in lift mode, which is, I think, up to date still the most common way of measuring KPFM. You can already distinguish different layer thicknesses. For example, dark spots usually correlate to a higher number of stacked molybdenum disulfide flakes, and brighter spaces to less stacked, fewer stacked membranes. And we see a potential difference between the silicon place and the molybdenum disulfide of roughly 357 microvolts. However, here at Park Systems, we can do slightly better, and we can, although with just a few clicks, choose to measure in sideband KPFM. That allows us to already see quite a lot of more details. For example, we can already distinguish different blisters and cracked solvent molecules within the tear films. We can distinguish contaminations, and we can see very sharp and distinct features between these different layer thicknesses. We can even identify strain within these films. And we see a potential difference between 550 millivolts between silicon and molybdenum disulfide. So in general, we achieve a high spatial resolution and electric sensitivity. And we achieve that by using a rather small AC frequency of 2 to 5 kilohertz. And in a process called frequency mixing, we modulate the first mechanical resonance peak of the cantilever, creating left and right two sidebands. Our KPFM feedback now does not minimize the amplitude at the driving frequency, but instead minimizing the amplitude of these sidebands. This had the advantage that the sidebands directly correlate to the electrostatic force gradient, not the force itself, which has a far shorter range, which means we can basically get rid of the background electrostatic influence of the cantilever beam and only see the signal, or mostly see the signal, between the tip apex and the sample interaction. One example, or the first example I would like to show you, we've done such measurements where to study the quality of a graphene single film on a Sapphire substrate. And our collaboration partners at Algstrom developed a synthesis routine where they could directly synthesize graphene films on a Sapphire wafer, which is a milestone, as you're well aware, since Sapphire wafers are widely used in the industry. So this could pave the way to future applications where we don't need to transport the graphene films, which introduces defects and contaminations. Sorry, my throat is like sore. However, they realized when they, in the same reactor, in the same environment, introduce a previous etching step in a pure hydrogen atmosphere, they could introduce a Sapphire terrace structure. And any graphene film synthesizing on this terrace structure would then have a far fewer numbers of ridges and wrinkles within the graphene film. So the overall film quality would increase drastically. And they could also verify this using traditional peak spectroscopy and finding a very favorable peak ratio of 2D to D peaks, which usually indicates a very high graphene film quality. However, they, and we of course, were wondering how homogeneous the surface properties really were, especially how homogeneous the work function and mechanical properties were, especially in this wrinkles and ridges, because they are very expected to influence the properties. So in order to study this, we measured KPFM and graphene in air and mapped both the topography and the surface potential. And then we zoomed in on specific regions of interest that show these wrinkles and elevated features. And here we found that higher topography usually coincides with a lower surface potential at these wrinkles or Sapphire steps. We usually measure this with our standard research tool, the Park NX10. However, we were wondering if these lower surface potentials stem from water infiltration or a weaker substrate interaction at these Sapphire steps, or maybe even a strain locally in the graphene, which also makes sense. So to get rid of the influence of water, we conducted this kind of measurements in an additional setup using our Park NX HiVac, which allows us to conduct easily measurements in pressures below 10 to the power of -5 millibars. So we again focused on these regions where we saw those wrinkles, zooming in, and we found the same features, that we have usually elevated features that show lower surface potentials. We could basically verify that the contrast we are seeing are not only caused by water infiltration. So we are wondering, is this due to a weaker substrate interaction or simply, or strain basically, locally that we see in the graphene film, because we would expect that strain would also change different properties, especially the mechanical properties, because strained graphene films are expected to be slightly stiffer. So in order to map the mechanical properties, we used a mode we call pinpoint mode, where we basically measure isolated force distance curves for each pixel on an area, and basically generating this set of force distance curves for each location, which allows us to easily identify and discern, for example, very soft and sticky areas and very hard and rigid surfaces, for example. And such simple force distance curves are usually conducted by simply approaching the cantilever to the surface until the attractive van der Waals forces pull the cantilever towards the surface in this snap into contact regime. Then we press further down until we reach a previously defined set point force, upon which we then retract again until we snap off the surface and separate entirely. And from this rather simple experiment, we can already derive, as you're well aware, quite a lot of information. So we can, for example, read the topography, but from the force needed to detach, we can also already read out the adhesion. But we can also get different properties, for example, the deformation, so basically how squishy our experiment is or sample is. We can read out from the difference in set separation between zero force applied and maximum force applied. We can also calculate the adhesion energy, which is sometimes important for the surface energy in wetting processes, for example. And we can call other values, for example, the energy dissipation, or more importantly, from the slopes, we can calculate the stiffness and the Young's modulus. And we did exactly that on these graphene films in air, comparing the adhesion force with the modulus, comparing it with the surface potential. And here we found an interesting correlation. We found that mechanical features usually correlate with the potential. So we found a lower surface potential at these wrinkles and steps that coincides with a lower adhesion and a higher Young's modulus. So we are, So we are pretty sure that we did have strained graphene and probably a weaker substrate interaction. So another field where we can use, or where FM is widely used, of course, solar cells. For example, this is a perovskite solar cell that I synthesized a while ago. As you can see, we have these 6 different functional layers. And the name-giving element, of course, is the perovskite layer that absorbs light, producing charge carriers. For the function of such a solar cell, we desperately need to understand how the charge carriers are transported through the different layers. So we need to map this also locally, because as you can see, we have quite a lot of topography that can influence our experiments. For that, of course, we can use conductive FM that we also have heard today, where we basically map our surface in contact mode while applying an additional bias and measure the flow of current with a current amplifier. So we can not only map the topography, but we can also map and distinguish high conductive areas, for example, to low conductive areas. And here, Boxosyms, we can further customize our experiments and choose between different current amplifiers. So our internal current amplifier already let us image 6 orders of magnitudes of different currents, basically coming from 10 picoampere to 10 microampere, with usually a noise level of below 1 picoampere. But we can also further expand this regime using a variable gain external current amplifier that lets us to image currents up to 10 milliampere with a noise level of 0.3 picoampere. And we can measure very ultra-low currents with our ultra-low current amplifier with a noise level of below 0.1 picoampere, and let us measure currents in the femtoampere regime, basically. This is all nice and dandy. However, when we want to image very fragile samples in contact mode, this can cause problems sometimes. For example, this is a perovskite film that was additionally coated with a polymer for preservation and humidity resistance, since these layers are quite sensitive to ambient conditions. However, in order to measure any meaningful current, we need to apply very high pressure to penetrate this insulating polymer layer and get to the perovskite layer. When we measure this in simple contact mode, we would simply drag away the polymer and smear out our signal and destroy our sample, and in worst case scenario, also destroy our cantilever. In order to circumvent this, we can combine conductive FM simply with pinpoint and locally probe our conductive properties. So this, as you can see, measurement done in normal contact mode, conductive FM. You see quite a lot of stripy signals, quite out of smeared signal, and overall a very poor film quality. Pinpoint mode, we can, on the same area, by the way, before the contact mode, we see very crisp and sharp features and very distinguished and very nice current images. Plus, of course, we get the mechanical information, for example, local adhesion that can allow us to discern local contaminations or energy dissipations. It's quite interesting. However, we can do more. As you're well aware, a semiconductor usually has a valence band and a conduction band that are separated by a band gap. When we illuminate this semiconductor with defined laser pulse, we can promote electrons from the valence band into the conduction band, where these excited charge carriers act as free charge carriers, increasing the conductivity of our materials. After a certain time, they decay back into the valence band, and the current accordingly drops. We can combine this with atomic force microscopy to map and study the charge carrier properties locally and time resolved under the tip. For that, we use our so-called photocurrent mapping mode, where we basically monitor the applied bias and the measured current as a function of time. So basically, we first apply a very small negative bias to remove any residue charges. Then we apply a positive bias to establish a flow of current. When we then switch on the pulsed laser, we create a lot of excited charge carriers, increasing the flow of current. When switching off the laser, this current then decays to its original level without any light, basically. And this decay already yields quite a lot of information about recombination rate, trap density, for example, and other crucially important properties. So this allows us basically to map locally in time resolved the current of different semiconductors or light-absorbing materials. However, we could also use these simply to increase the number of charge carriers by having a higher light intensity to also be able to measure very low conductive materials. For example, we have basically 3 sources of light we can use to illuminate our samples. We have the white light in our camera LED setup. We have 3 different laser modules at 785 nanometers, 635 and 450 nanometers. Plus, we also have the superluminescent diode to observe our cantilever movement, which is at 835 nanometers. So basically, we can choose and customize our experiment to match it to the ideal absorption spectrum of different absorbers. For example, in a recent experiment, which unfortunately I can't show you today, I mapped basically a tandem solar cell made of silicon solar cell and perovskite solar cell, where I only illuminated the silicon part by using just the superluminescent diode, basically. So I could map the trap density within the perovskite film while not being illuminated. Quite interesting. But instead, I've shown you simply another experiment, how this would look like in our optical setup when we use different LED intensities to illuminate our sample. We can, of course, also switch off the superluminescent diode to be not affected by any light. And we could use either just the PCM laser or switching everything on for superluminescent, for super illumination. Such an experiment we did, for example, at methylammonium lead iodide, the flagship of perovskite solar cells, where we saw basically different steps of current flow according to the light illumination achieved by the LED. However, in some cases, for example, like the polymer-coated perovskite layer I showed you before, this was not enough. Even at 100% LED illumination, we didn't see any flow of current or hardly any flow of current because it was so low conductive. However, in combination with the superluminescent, with the laser module, we got very nice different conductive domains and could identify basically isolating pathways in our perovskite. And of course, we can switch the laser module off and on, doing one measurement at free will. The last example I would like to show you today are layered heterostructures and 2D materials. And as you're well aware, the most famous example for this, of course, is graphene, which has gained a wide range of interest in the last 15 years, I would say. And like any other 2D material, we have very strong in-plane bonds and very weak out-of-plane bonds due to van der Waals interaction. However, we find quite a lot of different other materials that share a similar structure. For example, hexagonal boron nitrate, HBN. Here, instead of carbon atoms, we have alternating boron and nitrogen atoms in a plane. However, although they do share the same structure, we have vastly different properties, as you might know. Graphene is highly conductive, and HBN is basically an electrical insulator. But we can tweak the properties more of such layered structures by simply stacking 2 layers on top of each other, either with or without a twisting angle, creating new properties simply due to a modulation in the atomic registry. For example, the famous example of the Moiré pattern that emerges by this twisting angle and becomes smaller and smaller with increasing twisting angle. We can image, of course, such Moiré patterns in different physical properties. For example, we see it in the phase of the tapping mode measurements. And this is a nice example where this blister created local strain in the graphene film, which also influenced the pattern. So we saw different repeatabilities in these Moiré pattern. But we can also see it in the local friction measured by lateral force, or of course the conductivity locally, also modulated by the atomic registry. In the last experiment, we didn't observe Moiré patterns, but we found a very interesting other feature. We found ferroelectric domains in a bilayer of HBN on graphene. And although the topography was not that interesting, we saw quite a lot of modulation in the surface potential of these films. And these stem basically from the polar bonding of this HBN layer. So in the bulk material, for example, each boron atom is usually neighbored by 2 nitrogen atoms of the layer above and below. So, and the polar bonding or the dipoles emerging from this polar bonding basically cancel each other out. However, if you introduce a parallel stacking, this is no longer the case, and we get basically unpaired dipoles that create a net electric field, which we can observe and which we can also manipulate. So in this experiment, we basically fabricated these devices, saw this very nice feature in the surface potential, and we then used pinpoint mode and applied constant bias, basically to switch the domain orientation. And we used pinpoint mode in order to avoid any lateral shear forces to not twist the layer orientation. And we could see that when applying a positive bias, we could have one favored direction, and when applying negative, we could see the other direction basically being more prominent. But we couldn't do this only once, we could do it in a sequence of polling on the same location. So we basically measured KPFM, applied +3 volts, KPFM, -3, and so on. So on the same location, we get a switching forth and back. So this demonstrated quite nicely that we can introduce switchable ferroelectricity in thin film applications that might pave the way for electric field dependent doping, for example, in new thin film transistors. But with this, I really would like to come to an end, and thank you very much for your kind attention. And if you have any questions, feel free to ask or send an email at parksystems.com, pse@parksystems, and thank you very much.
Yeah, thank you very much, Alex, for this nice introduction into the different techniques that we can use with AFM. So we're open for questions now, if anybody has some.
Thank you very much. Beautiful talk, beautiful images. I have 2 questions. The first one is general. You mentioned in the slide magnetic measurements and MFM. I was wondering if you could comment on what is the direction your users are going to in this field. The second relates to this adhesion. You had these correlations between different types of maps. I was wondering actually how surprising that is to you, given that you're using the same data to infer all these different maps. And I guess you would probably have very different noise levels on these different images, depending on the model that you on the equations that uses your single equation, your single model.
Coming to your first question about MFM, magnetic force microscopy. So for that, we usually use a cantilever that is evaporated with an additional magnetic coating, usually a cobalt alloy or something like this. And this is surprisingly widely used in industry for mapping and doing failure analysis of storage devices, where we also have very fine magnetic domains that we can basically then use for example, hard disks. So this is used basically. Also, this is quite important for an emerging field of spintronics and skyrmion, basically based storage devices. So there's actually a surprisingly huge market for that, although it's a niche application for AFM users. Concerning the quality of these data, these measurements were done in different modes. So KPFM is usually doing in a so-called non-contact mode, where we don't touch the surface at all. We oscillate the cantilever, and we avoid interaction mechanically. The mechanical data, however, we really slowly press down on the surface and map the cantilever deflection. So these are 2 separate measurements with 2 separate sources of noise and quality, I would say. So it's, I mean, from the scientific standpoint, it's no wonder that we see different mechanical features and surface potential features on these grains, because this is how graphene works. From the measurement stand view, it is nice to see that we can basically with individual measurements see similar effects. As for the quality of the mechanical data, we can choose between different models to basically calculate the elastic modulus. So we have this JKR model, as you're well aware, maybe we have the Hertz model for very hard and rigid surfaces, and the DMT model for maps, or basically for materials that have a stiffness basically between 1 gigapascal and I think 10 gigapascal. So we can choose during the measurement which model to use to calculate the features. We can, after we did the measurements, also use different models. Even with Gridion, we had a collaboration with Gridion that allows us to choose in post-measurement the different models to calculate the values. So I would say these values are usually quite reliable, because also we have the standard way of calibrating the cantilever. So it's quite nice. I hope this answers the question.
Thank you very much.
Yeah.
Yeah, thanks for the impressive results you showed. I just have a rather specific question regarding the photoconductivity measurements you showed. Specifically for this perovskite stuff where you had this rather conductive and rather poorly conductive regions. I guess you contacted the sample from the backside for the, let's say, bias, sample bias. And then my question is, how thick was the sample? Because if you have these lowly conductive regions, it's most probably if you go deeper or have a thicker sample, you wouldn't see anything anymore.
Yeah, so first of all, which kind of substrate were those? These were usually FDO, fluorine doped tin dioxide. And the layer were usually 200 micrometers in thickness, but it's transparent, so it's widely used for solar cells. The perovskite film itself usually had a thickness between 300 nanometers and 500 nanometers. So the mixed, we call this cation mixed approach, which usually allows us to shift the band gap of these perovskites due to orbital bond. And these perovskites are slightly thicker, usually 500 to 600, 700 nanometers. These non-conductive domains you see here are quite frequently in perovskite solar cells. And up to now, it's still debate where these domains originate from, at least to the best of my knowledge. This is, in my point of view, mostly surface phenomenon. So if the film is 300 nanometer thick or 600 nanometer thick, we see in both cases these domains, and we see the number of domains and the size of domains increasing when exposed to humidity. So in perovskites, you have these hexagon, these octagon structures, basically, there's three-dimensional networks. And in the cube octahedral vault, you have the cation. However, when water gets to the surface, this is a stepwise degradation process we see. And the first process is that we basically isolate these single octahedrons and form basically a small substructure where this octahedron is surrounded by water molecules. So we basically, at the surface, swell the structure and it becomes insulating. And I think this is what we see here. However, this is still an ongoing debate, and there are probably other factors, because in very fine, pristine films, we also see sometimes these domains that have never seen any water at all. Though also the problem is in these perovskite films, you have quite a lot of mobile iodide ions. So when you apply an electric field, these ions can migrate, creating vacancies that again also can degrade the structure. So it's not that easy to answer.
Thanks. Just a short second question, because I'm also quite curious about your time-resolved measurements. Unfortunately, you couldn't show something. Yeah. Is it just a new feature, or do you have any data to show? I mean, not in this talk, of course, but later on, I would be quite interested in.
If you write us an email, we come gladly back to you.
Okay.
Unfortunately, so far I can't show you any data that is
okay.
Where the solution to public.
I understand.
Just on that slide, you have this 80% step there, and it seems to be a rise at the edge of the step, which can't be seen on the other steps. Is there an explanation for that?
Yes. This can have several factors. One, for example, these perovskite films are again quite prone to degradation by humidity or other effects, and usually this degradation is catalyzed by a high photointensity. So you have more light, then the degradation process is accelerated. And what I can imagine that the colleagues that did these measurements didn't measure in an inert atmosphere, but in air. Basically, what we see here is the first effect of these migrating iodine ions that cause an initial shift in migration of ions, so basically also a current, but then rapidly comes to a halt and start to degrade the structure. So I think if we would increase then the intensity to 100%, or even use additional laser light, we would probably see a rapid decrease of current over the time. But again, there are quite a lot of factors that play individually a role and affect the perovskite solar cells, which is the reason why we don't see yet any commercially available structures. But several approaches try to tackle this problem, for example, by sandwiching the perovskite layer in between very thin layers of polymers, like shown before, to stabilize the system, or using different absorbers, for example, that are not based on iodide, but either on bromide, which has a larger band gap, which you but use combined to tandem solar cells, or using a 2D approach where we would additionally break this three-dimensional network intentionally using very large organic cations to have something like hydrophobic blocks in between to stop the progression of water within the structure.